Welcome! There are two goals to this lesson. The first is to help you get better at implementation. That is, you'll get better at converting your ideas into code, and you'll be able to think in a way that makes the process of coding your thoughts to be much easier. And the second goal is, if you aren't already familiar, to get you familiar with programming and the logical mindset of programming, so to speak. If you're already familiar with programming, then you can skip over that part using the timestamps in the description, and you can skip to the announcements section right now. But if you aren't familiar, it won't take that long to grasp the fundamentals, and we'll start off with C++. And as C++ isn't your target language, it doesn't really matter much. You'll find that most programming languages have the same basic logical structure, and while there may be small differences in the exact details, you'll be able to apply the same kind of programming style logic to everything. The programming language you use isn't really important. It's more about thinking in a way that makes it easy to code, and I'm going to teach you that in this video. So we're going to use C++ mainly because it's the language I'm most familiar with, but it'll easily translate to whatever language you want to use, like Python, JavaScript, or anything else. But before we start, I have some important announcements. And you can skip these if you really want, but I think they'll be beneficial to hear, especially the first one. And the first and biggest announcement is that the website, AlgoLens, the one that debugs your code for you, that one, is complete. And if you don't know what I'm talking about, check out the site's homepage, which is linked in the description. You should definitely check it out. It's very cool. It changed your life, maybe, probably not, but yeah. And feel free to make some test submissions and make an account and stuff like that because I want to load test the site. Second announcement is that I made a full Discord server for AlgoLens. You may have already seen this because my previous Discord server has been long dead, but this one will probably be more active and will be dedicated to the website and the course material. So you can come in to ask questions, report bugs, suggest improvements, or just chat about whatever. You can find that link in the description. And the third is that I've opened to Buy Me a Coffee. It's essentially Patreon, but it supports stuff like UPI, so you guys in India, which is the vast majority of you, will have an easier time. And this is because some people have expressed interest in supporting me and or the website, so I've just opened up a way for people to do that. You can find that link in the description too. Everything's in the description. The money will go first towards server costs if necessary, then toward improving the channel with stuff like hardware, maybe a better mic. You'll also get a better special supporter role and exclusive channels in the AlgoLens Discord, which is also why I wanted to open a new Discord since the role system in the original one is a complete mess. I may also experiment with YouTube memberships in the future since that's easier, but Buy Me a Coffee gives me a 95% cut, so I'll stick with that for now. Now let's get back to the lesson. To prove my credibility, and I do this at the beginning of every video, here's my effective resume in terms of competitive programming. I have about 3 years of experience in competitive programming, and I reached the rank of International Grandmaster on Codeforces and 7-star on CodeChef. In terms of Google stuff, I've gotten to round 3 in CodeJam twice, and my best rank in Kickstart is 10th, which by some coincidence also happened twice. And I also have 1.5 years of experience talking at a screen, just like this, so I've gotten pretty good at explaining this kind of stuff. So yeah, the point of this resume is not to flex because there's not really a point in doing that. I just want to say you can trust me. I know what I'm talking about. I'm not going to mislead or confuse you. This lesson will be accurate, well thought out, and complete. And with that said, let's get into the actual lesson now, finally. But one more thing, sorry. Before we start the lesson, let me just give you a quick overview of how this will be structured so you know what you're getting into. We're going to start with the intro to programming, going over a way a program is usually structured and the basic building blocks of logic in a program. You'll get enough info to be able to do basically anything that a program can do that I won't be able to fill in all the little details because if I did this video, it would be multiple days long. But yeah, if you want to skip that, there are timestamps in the description. You can just check those out. And after that, we'll take a deep dive into implementation with various tips and a general method of thinking that will make coding a lot easier. And after that, we'll do a bunch of example problems to practice with that method and the tips. Okay, now let's actually start the lesson. This is the intro to programming, and I've said before, if you want to skip this, go to the implementation tips section in the description. So programming is, in essence, telling a computer what you want it to do. And computers don't work like humans. You have to be extremely specific in telling it what to do, and it will do exactly what you tell it to do, no matter how many mistakes you make. So however much you fill in the blanks about the actions you take in your life, you have to get more specific when you're talking to a computer. For example, let's say you have to go shopping. For you, the way to do that is pretty simple, right? If you were tasked with going shopping, you would immediately know what to do and how to do it. There might be some parameters like where and what to buy, but in general, you'll know what to do. But a computer doesn't. If you told a computer to go shopping, it would stare at you with a confused expression and not do anything because it doesn't know what to do. Go shopping has no meaning to it. Again, you have to be extremely specific in what you tell the computer to do. So a program for shopping would be more than go shopping. For example, it could look like this, and this is a complex set of instructions. You obviously don't have to read all of this. This is just an example. There are certain things that the computer automatically knows how to do, like adding two numbers, or walking, or driving, or picking up an item, and you don't have to worry about how to do that basic stuff. But for everything else, you have to break your task into small enough pieces that the computer automatically knows how to do each piece, or you'll get nothing but confusion from the computer. So these are the guiding principles we're going to follow. When you're talking to a computer, you have to be specific, and when some part isn't specific enough, break it down into more specific parts. And if you're ever confused about how to program something, these guiding principles will help you make it simpler for yourself. So a programming language is the language you use to talk to a computer, just like you talk to other people, like I'm talking to you in English right now. You would talk to a computer with a programming language. It's just what you would expect from a language. It's just a way of talking to computers. Our language of choice for this video, as I mentioned, is C++, and it's a pretty powerful one. As you become familiar with C++, you'll also become familiar with the way a computer thinks and the exact set of tools that C++ or any programming language will give you. The beginning stage of programming is roughly equivalent to putting every sentence through Google Translate when talking to someone in a foreign language. You aren't going to be familiar with how to do everything, and that's expected. That's why you have the internet and the documentation and Stack Overflow and AlgoLens even to help you out when you're stuck and don't know how to do something. And it'll take a while to get familiar with stuff, but once you do, you'll be able to program as easily as you can speak your first language. Or maybe not, but eventually your problem won't be how to complete a task in your programming language. It'll be how to frame the task as something a computer is capable of doing at all. So let's get into how we do that. The general flow of a program is not too difficult from your general flow of thinking. It's just a lot more detailed than you may be used to. So let's start with a simple problem to illustrate how this works. Your task is to add 3 and 5, which is simple, right? But this is a good example of how things work in the C++ world. First, for any logic you want to execute, it has to be done inside this function called main, which has to have an int before it. More on functions later in this video. They're basically just isolated boxes of code, but right now the rule of thumb is that every basic line of code should be inside these brackets. But there are also exceptions to this rule, as with everything that we'll go over later. And with every programming language, we use these things called variables. Variables are just locations in the computer's memory that store things. For example, we can store numbers, or letters, or lists of letters, or lists of numbers, or a special type of variable called a Boolean value, which is only either true or false. And there are a lot more data types, and you can even create your own custom data types that contain other data types, but I'll leave all that to you to research on your own. In this case, all we want is a number. An integer would be enough, since we don't need a decimal point, so we'll use that. Creating a variable is called declaring it, since we kind of declare to the computer that we're going to use a variable with the name we choose. And also, every meaningful line has to end in a semicolon. That's just the C++ rule. So here, inside the main function that I mentioned earlier, we'll declare a variable called sum. Then we want to add 3 and 5 and store the result in sum. So we'll assign the value of 3 plus 5 to sum, like so. Note that this is different from what the equal sign means in math, for example. Sum equals 3 plus 5 means that we're giving the value of 3 plus 5 to sum. So now the value of sum is 8. And that's it. We've done it. This is the program. But how do we actually run this program? First, you have to compile it. And compiling a program is essentially converting it from the C++ language you know and love to an executable file that a computer can easily run. You're probably familiar with executables. But yeah, once you have this executable, you can just run it like any other application. To get a C++ compiler, such as, for example, G++, you can search it on Google, and you'll find a million tutorials on how to do it, so I'm not going to cover it here. Have fun with that. Now let's do more. We added 2 numbers, but then we didn't do anything with it. So our value 8 is just sitting inside the variable sum with no way to access it. So now, instead of adding 2 fixed numbers, let's write a program that will add any 2 numbers together and then actually tell us the answer. So how do we do this? Remember, when talking to a computer, it's not enough to just tell it to add 2 numbers. Remember the guiding principles. We have to tell it the exact steps that we want it to do and simplify our big task into a bunch of small, easily doable tasks. So how would this happen in real life? Let's say I ask you to add 2 numbers. What would happen? First, I would give you the 2 numbers that I want you to add. Then you would add the two numbers, maybe in your head or on paper, depending on how big numbers I give you, or whatever. And finally, you would tell me your answer. Now, our program's flow is going to be pretty similar to your flow when given this task. So the first thing we need to do is get the numbers we need to add. This is called reading input, where the input is the specific values that we give to the program, representing the task that we need to solve. In code, first, we tell the program that we want to include the built-in input and output. That's the top line. We have to do this explicitly because if everything was included, the process of compiling would take way, way longer because it would have to compile a bunch of stuff that you aren't even using. So we add this line to the top. It should be at the top and not inside main because of C++ reasons. Then we need to declare two variables representing the numbers that we want to add, for example, a and b. And then finally, we can read in the input into these two variables. This is done using cin, which is C input or just C++ style input, but it also actually has to be this thing called std::cin. And that is an example of a namespace. It's not really relevant to this lesson, so I'll leave it to you to figure out why those are useful. And std is for standard, as in standard library, which is C++ library of functions that you can use. That is not the only acronym that sounds worse when you say it. Have fun with that. And if you don't want to type stdcin every time, you can include this line at the top using namespace std. This means that every std function should be treated as a normal function, and therefore you don't need std::: everywhere. This is heavily not recommended in production C++ because huge code bases can have a lot of intersections of function names and get really complicated, but for this simple case, it's fine. So we read into a plus b using cin. And now we need to add the numbers. This is simple because we've already done that before. So we can declare a new variable called sum and store a plus b in it. And finally, we need to display the answer. This is called output, and it's the reverse of input. Instead of giving values into the program, we take values out of the program and display them. The way to do this in C++ is appropriately called cout. And it looks like this. It's simple. It's very similar to cin. So that's it. Those were our 3 steps. And note the direction of the arrows with cin and cout. It's kind of symbolic. With cin, the variables go from cin to the variables because you take input and then give the values to the variables. Whereas cout, you're outputting the values. So the arrows go from the value to cout because you're giving your values to cout to output. Now, how do we interact with this program? Here I have my command line open, and this is generally what we're going to do. My file is called aaa.cpp, which means, so I'm going to first compile it on the command line, and then like so. And that will compile it, and -o is the output file. So I'm going to compile it and tell it to compile to a file called target file. And then I can simply execute that file. And then this is the program to add 2 numbers. So I'm going to give it 2 numbers, and it will display the output. And that's how we run programs, and that's how we interact with it. When you submit this to an online judge like Codeforces, they'll handle the input for you and make sure your program gets it, and you just have to make sure that you read in from cin and output to cout. So now we know how to add numbers and interact with the user, and that's pretty good. But C++ knows all the basic arithmetic operations like subtraction, multiplication, division, and a bunch of other things that aren't really worth mentioning here. And I should note, C++ and every other language follows the standard order of operations that you're used to. So it'll do arithmetic exactly how you expect it to. For example, it'll do the multiplication before the addition, and it'll do equivalent operations left to right, and it'll do operations in parentheses first, all as you would expect. If you want a full table of the order of operations, including the non-arithmetic ones, you can search C++ order of operations and it to find it. But again, it'll mostly match with what you're already used to. So that's all cool, arithmetic. But what else can we do? There's still a lot more that we don't know how to do yet. For example, let's try to compute the absolute value of an integer. And if you don't remember what that is, it returns the value but without its plus minus sign. So 5 would become 5, and -5 would also become 5. There are a lot of uses for this function, and we don't care about any of them. Let's just code it. So something about absolute value is that it can be represented as a piecewise function. That means for certain values of x, it behaves one way, and for other values of x, it behaves a different way. In particular, for certain ranges of x, like x being positive, it'll return x, and otherwise it'll return negative x. So enunciating that again. If x is positive or 0, then x is already non-negative, so it just returns x because x works. And otherwise, if x is negative, then it has to make x non-negative, so it returns negative x because negative negative is positive. So we have this kind of if logic. If x is positive or 0, return x, otherwise return negative x. And this is pretty convenient because C++ has this thing called an if statement. It's structured like this. If something, or some condition, do something, and else, if that condition is false, do something else. So let's fill in the blanks for our absolute value. If x is greater than or equal to 0, our answer should just be x, and else our x is less than 0, so our answer should be negative x. And we've done input and output here. You should be fairly used to those already, so that's all standard. And you can even chain ifs, though in this example it's dumb to do so. But for example, say we wanted, for whatever reason, to explicitly set our answer to 0 if our answer was 0. We can have an if, and then if that condition is false, we can have a different if that checks a different condition. And it will behave exactly how you would expect it to. Awesome. So now we have some real logic. And just if statements in arithmetic are enough to handle a lot of possible tasks. But there's also still a lot we can't do. For example, we can't process multiple things. Say we're given a list of integers and we need to compute the absolute value for each of those integers. There's no arithmetic or if statement logic that can save us from this one. We need something else. And that something is loops. So there are two types of loops, but they're kind of the same thing, so we'll go over both of them quickly. The first type is a while loop. The structure of a while loop is simple. While its condition is satisfied, execute the body of the loop, and do that until the condition is false. For this problem, the condition should be that we still have numbers left to process. So while we're not out of numbers, continue reading input and outputting the absolute values of the input. So how do we check if we're out of numbers? And there are two ways to do this, probably more, but one of them makes for a better segue, so we'll do that one. The problem starts us off with a number n that represents the number of numbers we need to answer for. So we can keep a counter of the number of numbers we processed, and when that counter hits n, we know that we've gone through all the numbers. So we do this by starting the counter to 0 because we start by not having processed anything. And the while condition is while the counter is n, which means while we haven't processed all n numbers. And inside the loop, we process a number, and then once we process a number, we add 1 to the counter to indicate that we processed another number. And processing a number is pretty simple. We've already done that, so here's the full solution. I just copy-pasted absolute value into that because it's the same problem. And this should all make sense, and this works. It'll solve the problem. While loops are fine. But this is kind of annoying because the loop is really split into 3 parts. We have this initialization part at the beginning where we set up the counter to be 0. And then we have the loop condition itself, and then at the end of the loop, we have this modification part where we update our counter after each iteration of the loop. But what if we can just put all these parts next to each other, and that way we don't have to keep track of them, and that way they won't be so separate every time? That would be nice, right? Well, that's exactly what a for loop does. A for loop is structured like this. Before entering the loop, it runs some initialization statements. At each iteration of the loop, it checks some condition. If that condition is true, then it continues going through the loop body. And after every iteration of the loop, at the end of the loop, it does some modification process. It's actually exactly equivalent to our previous while loop structure. And notice that if we just leave the initialization and modification out, a for loop is exactly equivalent to a while loop. It's just for condition, which is equivalent to while condition. So you would generally use a for loop for most cases, but you could switch to a while loop when the modification part is complex or more than one line. And the main difference between the two loops is generally how we think about them. A while loop behaves like, while the condition is still true, continue going through the loop body. In this case, it's while we still have elements to process, keep processing. Or while our counter is less than n, keep processing. A for loop is more like, for each number between 0 and n-1, do something with that number. Or for each element in an array, do something with that element. In this case, it's symbolically, for each number that we have to process that number. But really, it's for each number between 0 and n-1, process one number, meaning we'll process exactly n numbers total. And in this section, I should probably talk about arrays too, since there's no other place to fit them. So the quick overview is an array is a list of objects. The objects can be any data type you want, for example, integers or characters. And to declare an array of ints of size n, you would use this syntax, int r bracket n bracket. where n is the size. And to access or modify the ith element, you would access r bracket I. And this is treated like any other variable. Arrays also start counting from 0 because it's convenient for computer memory. It'll make more sense when you know more about the language. And also, to be safe, you should not assume that array elements, or any variable really, have a default value, like for example 0 for integers. If you want the values to be 0, you should set them all to 0 before you start using the array. And also, arrays do have to have a fixed size that you specify before creating the array. If you want an array that doesn't force you to specify a size, you can use another data structure called a vector, which I won't cover here. Okay, if statements and loops are huge. You can do basically anything that you need using only those. But there's one more thing we'll cover just for convenience, and this thing is called functions. And basically, functions are isolated blocks of code. Let's take the absolute value example. In this loop, I compute the absolute value for each input number. But what if I wanted to use absolute value multiple times? I could copy paste this piece of code and put it everywhere that I need to use it, but that would be quite a pain. So instead, we can wrap this code into a function like so. On the top line in the parentheses, I have it set to accept the single integer argument, namely the value that we want the absolute value of. To the left, I specified that I'm returning an integer, namely the absolute value. And in the function, the special keyword return means that the function will stop and it will send the returned value to wherever the function was called. Then to execute this code, also known as calling the function, I can just ask for the absolute value of some x. And you can do anything in a function that you can do in main. A function can even call itself, which is a very powerful concept called recursion, and it's too complicated for this lesson, another time. And outside of this function, note that basically only the top of the function line matters. Outside of this function, we don't care how we compute the absolute value. All that really matters to us is the input to the function and the output, and the name, which specifies what it does. In this case, the input is a single integer, and the output is the absolute value of that integer. So functions let us completely abstract away certain sections of our code, and allow the code to be a lot less clunky in some ways. And there's one thing left to talk about for functions, which is convenient behavior called scope. The gist of that is, let's say I have a variable y in main. And in some function, I try to modify or grab that value of y. This will not work. As you can see, y is highlighted in red. Even my code editor doesn't like it. The reason is, when a variable is created, it's only accessible from the same group of brackets that it was created in. So y can only be accessed from the brackets of the main function. And this group of brackets is called the variable scope because it's the region of code that can access it. If you want a variable that's accessible from everywhere, you have to create a global variable like x, which has to be outside of every function and also above every function because order matters. I consider this a convenient behavior because if a variable isn't global, then no outside function can accidentally mess with the variable, so it can keep your variables safe from mistakes. And that's the main idea of scope. I encourage you to play around with this more to understand the behavior better, and even try and create two variables with the same name, one inside a function and one outside. You can see what happens. So now, that's the intro to programming. Here are some general tips that should help you out with implementation. We'll start with this, then I'll give you a general thought process you can use to make implementation easier for many problems. First, you should flesh out your idea. Break your idea into tiny little bits that are all easy to work with, and then code those little bits by themselves, as opposed to trying to tackle your whole idea all at once and ending up with a mess. If you're expecting a lot of, say, off by one errors, work out the math on paper before you write even a line of code. That will make it much more organized and it'll make it easier to follow. You'll be able to think about it better as well. We'll do a ton of examples on this process later in the next two sections. On top of that, you should debug not only your code, but your idea. You probably know this already, but this is just a formalization of it. It's perfectly possible that your code exactly matches your idea, but your idea is just wrong, and so your code is doomed to be wrong too. It's also perfectly possible that your idea is fine, but you have a mistake in your code. You should explicitly check for both. And debugging your idea can be very similar to how you debug your code. You should isolate each piece of the idea and make sure all the pieces are correct, then make sure they work correctly together to form the full solution, sort of starting small and building up. Find the first point where something goes wrong or deviates from the expected answer, and look hard into that point and figure out why that's happening. You should take your time with both thinking and coding, because if you rush through every single detail, with very high probability, you're going to get some of them wrong. Many of the little details should ideally be clear before you even start coding, but even so, make sure your code does exactly what you expect it to and your idea works exactly as you expect it to, and take your time in doing so. And you may argue that in like a contest or an interview or something like that, every second counts, and you should prioritize speed over being careful. But what often happens is that you spend more time figuring out the details that you got wrong than the time you would have just spent by getting the details right by just being careful and not rushing. So being careful might make you slower sometimes, but ultimately you'll be a lot more consistent. And finally, often you should think about how to simplify your idea. If you know something's going to be long and complicated, spend some more time trying to think of an alternate solution that will be simpler, even if you already have a solution. And it's really hard to do that when you already have something that's correct, but it is absolutely worth it. I would say right now, my own number one weakness is not doing this enough and getting trapped in overcomplicated ideas when there's a simple one right around the corner. So you should definitely try it. Take the time. Think about how to simplify your idea, even if you already have something, because it could just be too complicated and you'll end up wasting a lot of time pursuing it. Okay, let's do more now. This next bit will be a general strategy that you can apply to basically any task. And it's pretty simple too. I mean, it's 3 lines, you can see. The gist is start with the full task. And while you don't know how to implement everything, pick some part that you don't know how to implement and break it into easier parts. Sometimes the breaking down of a part is what makes the task difficult, and being able to break it down takes a lot of thinking and mental effort on your part. But in general, that's the path you should follow to get to your code. And this is pretty much what we did when we figured out the structure of the A plus B problem. And if you skip that part, don't worry, it's self-explanatory. We started with the whole program and broke it into different pieces that were all pretty simple to solve. And for people who like arrows, you can call this the top-down approach. You start with the full program and get progressively simpler and simpler until each part is so easy that you immediately know how to do it. And that's it. Remarkably simple, right? But I imagine that this is not the thought process that most people follow when they're coding up a task. Because the easiest strategy to follow, and the trap to fall into, is identify the first part of the program that you need to implement, and then implement it. In the A plus B problem, you can say that input is the first thing you need to do, so do it. Then you should add the numbers together, so do that. Finally, the only thing left to do is output the answer, so do that. And again, for people who like arrows, you can call this the sideways approach. You start on the left with nothing being done and gradually implement things until you're done and on the right. And this works, and it's fine in many cases, but it's not going to go so well for more complicated tasks. The top-down approach will do better in practice because you're not only thinking about each part, you also end up thinking about the big picture and how the parts fit together. With the sideways approach, you take on each part one by one, and while you'll probably make each part work on its own, your solution will be more messy and disorganized because you gave less thought to the overall structure of the program. The top-down approach effectively forces you to think about the right things throughout and consider the entire flow of the program as a whole and the big picture, instead of making it up as you go along. Ultimately, you'll think about the same stuff either way, with the top-down approach or the sideways approach, and you'll use the same amount of effort, but with the top-down approach, you think about it in a way that makes more sense. And there's not much more advice I can give you, because again, no matter what, you'll have to expend the same effort. Ultimately, you're limited by the power of your own mind, and any particular strategy can only take you so far, but the top-down approach will be easier to use, and your code will just end up being cleaner and your idea will be cleaner. And there's another advantage to the top-down approach as well. You have the ability to take a step back and try to simplify certain parts of the idea. Because, as I've said before, it's easy to get trapped in a complicated idea just because it works, while there may exist a much simpler way to do things that you just haven't seen yet. With the top-down approach, all the coding happens after all the planning. All the planning happens before. So mid-planning, you're able to try to simplify certain parts or even the whole program. And since you haven't coded anything yet, you've expended less effort. It's harder to get trapped in the sunk cost fallacy that prevents you from switching out of an idea that you've already put a lot of effort into, even if that idea is stupid or complicated. You can realize that the idea is overcomplicated while you're planning it out, rather than while being in the middle of coding it, and you'll expend less effort overall. So yeah, that's my recommended method of how to think about your ideas in a way that ultimately makes it really easy to code them. So now we'll do a few problems to really dive deep into how this method works. I've tried to choose structurally different problems so you can get experience with different types of solutions with this method. And they're going to be pretty simple, but ultimately you can apply this to anything. So this is just a demonstration of how to use the strategy. So the first problem is you're given a list of points on a 1D number line and a target point x. You want to find the closest point to x and output the distance from that point to x. So pause the video and try that out. Okay, so let's break down how to implement that. First, we can use the input processing output model. So to read input, we need to read in the number of points and also x, and then we can read in each point, and we can do so into some array of points. And now we need to process each point, meaning that for each point, we need to do something with it. Generally, the strategy to find the largest or smallest of something is to maintain a current best answer and update it each time we find a better answer. So let's initialize our shortest distance with infinity because we currently haven't looked at any distances, so we have no estimate of what the shortest can be. Then for each point, the first thing we should do is find the distance to x. If this point's coordinate, let's call it y, is greater than x, then the distance is just y minus x. But if it's less, then it's x minus y or negative y minus x. And that's enough for a solution, but we can also notice that this is just the absolute value of y minus x, and we've done absolute value before. So we can apply the previous code that we wrote earlier, or just use the library's built-in function if you skipped the how to program part. And pi in this case is the ith point, or the value of y. And once we have the distance, now we want to see if this distance is better than the previous distances. If so, then this distance is now the shortest distance, and otherwise it doesn't change. So ultimately we update shortest with our current value, and we either change it or it stays the same. And after we process all points, the final task is output, but that's simple because we just need to output a single number. And here's the code for that. It should be pretty self-explanatory. You can pause and look at it or check it out on the site if you want. Okay, next task. This is also on a 1D number line. Imagine you start at location 0. At second 1, you'll jump 1 unit forward. At second 2, you'll jump 2 units backwards. At second 3, you'll jump 3 units forward. At second 4, you'll jump 4 units backwards, and etc. It keeps going, forward and back and forward and back. You're given a location x. Find the first moment in time where you're at position x. So again, pause and try that. Still frame. Okay, first, the coordinates are up to 10 to the 9th, which is a huge number. So you can't just simulate the jumps because there are way too many of them. And okay, so this problem is hard until you draw out the coordinates. At second 1, you're at location 1. At second 2, you're at location -1. At second 3, you're at location 2. At second 4, you're at location -2. And this pattern continues, 3, -3, 4, -3. Because if you pair odd and even jumps together, you can realize that you just jump backwards -1 units every 2 jumps. So how do we reverse engineer this pattern? We alternate between positive and negative coordinates, so we should probably treat them as separate cases since we'll have different formulas for them. And we can include the obligatory input and output, but they aren't so important here. So positive and negative cases. For positive numbers, let's just try it out again. We'll visit them in seconds 1, 3, 5, 7, etc. So in general, creating a formula for this, the first time you're at location x is time 2x minus 1. And for negative numbers, we'll visit them at seconds 2, 4, 6, 8, etc. So the first time you're at location x is -2x. So this problem gives us 2 cases. If the input is positive, we handle it one way, and if the input is negative, we handle it the other way. So ultimately, the implementation here is simple, but the idea may not be. And not every implementation will be difficult, but you could easily get lost in way more complicated ideas for this. This problem exists to encourage you to try to simplify your idea, because sometimes there's a really nice and easy solution right around the corner that you just have to take the time to look for. And here's the code. It should be pretty self-explanatory. Okay, final task. In this one, you have to implement a cache. And if you don't know what that is, here's a quick overview. Imagine you load a website. This website has an image of a cat on it. Now imagine you go to a different page on that website that has the same image of a cat. If your browser is smart, it will save that image of a cat locally on your computer. That way, it only has to load the image from the website once for the first visit. And on any future visits, it can just pull the image from the locally stored image on your computer instead of the website. And that can make the page load significantly faster since there's less the website has to do. But if your browser was to store every object you've ever downloaded, then that would be a lot of memory on your computer. So over time, it deletes the items that haven't been accessed in a while. And that's the gist of a cache. In this task, you're going to simulate the behavior of a cache. So your cache has n slots, where n is part of the input. You will receive Q items, or numbers, to download to the cache, and for each item, you should answer if it's already in the cache or not. If not, you should add it to the front of the cache at the highest priority, since you just accessed it, so it should have the highest priority. And if so, if it is already in the cache, then you should move it to the front of the cache at the highest priority, since again, you just accessed it, so it should have the highest priority. And if the cache is full once you add an item, once you have all n slots, you should remove the item at the back of the cache, which would be the one with the lowest priority. That's why priorities matters. So pause and try to code this. Okay, so how do we split this up? This time, our input and output is independent for each item. We start by reading the initial size of the cache and the number of queries, but for everything else, each item has its own section of input and output. So our input processing output stuff should happen for each item independently. But at this point, we should choose how we store the items in our cache. A simple way to do this is to have an array of size n+1. We can initialize the elements to some value like -1 to indicate that there's no element in any position yet, but this is ultimately up to you how you implement this. The extra element, n+1, is because it'll be convenient for intermediate calculations, and you'll see why later, even though there should only be n elements in the cache. And how do we process? Well, I've sort of given you the if statement logic already, since I kind of had to for the statement. So the first thing we do is check if the item is already in the cache. Constraints are small, so we can afford to naively check each element of the cache to see if it's equal to our current item. I don't have space to put that on the diagram, but that's what we do. We check each element and see if it's equal. And if so, we found the item in the cache, and if not, we didn't. And then we can output that. And afterwards, we need to update the cache with this item. So if this item is not already in our cache, we need to add it to the front of the cache. We can do this by moving each other element in the cache a position backwards, leaving the first spot open for the new item. That's how we insert it into the front of the cache. And note, by doing this, we don't change the relative order of the rest of the elements, which is the correct thing to do. And this just works. If the cache was full, then the item in position n, which is the lowest priority that should be removed, will be in position n+1 by default after we shifted it one position backwards. So we can just reset position n+1 to -1, effectively removing the item from the cache. And if our item is already in the cache, we can move each element that's higher priority than this element backwards to leave the first spot open for the item. Note that by doing this, we don't change the relative order of the elements, again, which is the correct thing to do. And that's it. We have these two cases, and that's all we need to do. So here's the code. It should be pretty self-explanatory. Yeah. And anyway, that's about it. While these problems are pretty basic, since it's sort of more of a beginner-oriented video, this advice can apply to everything. So I encourage you to go out and try some difficult implementation problems with this technique. For example, you can go in code forces and solve problems with the implementation tag. I'm sure there are plenty. And that's all. Goodbye.